Okay, so that's great. Well, let me tell you all, it's my pleasure today to host Mollie Schwartz, who I've known for quite some time. She graduated as a salutatorian from her class from Columbia University with a BA degree in chemical physics. Following that, she earned her master's and PhD in physics from the University of California at Berkeley, and she was also a recipient of the Goldwater Scholarship and Hertz Foundation Graduate Fellowship Awards, among many others. Currently, she's an assistant leader in the Quantum Information and Integrated Nanosystems Group at MIT Lincoln Laboratory. She is leading programs and pursuing research in the area of superconducting quantum technology with a focus on 3D integration and quantum algorithms, very similar to the kinds of things I used to do. So I'm very happy for her to go into detail about the kinds of importance that 3D integration has when you're taking superconducting qubits and fabricating them for scalable architectures. So Mollie, it's my pleasure to have you here today. Please take it away. And if you have any questions, please drop them in the chat. Sorry.
That's all right. Thanks so much, Nick. It's really good to see you. And I'm really glad to be here with all of you today to tell you a little bit about our work at Lincoln Laboratory, developing 3D integration for superconducting qubits. So first, I want to zoom out a little bit and remind ourselves of the computing development timeline for classical computing. So classical computers are now well over 100 years old. The vacuum tube was invented in the early 1900s. And over the lifetime of classical computing, there have been a variety of technology developments, some of them more sort of sequential, some of them revolutionary, like the invention of the transistor in the 1940s. And so over the course of the last 100 years, this technology has completely revolutionized the way we live our lives. Quantum computing is much younger. It was proposed as essentially a physics experiment in the early 1980s by Richard Feynman. And in the early 1990s, it was realized that there are actually a number of algorithms that one could run on a quantum computer that would be really interesting and very valuable. And this set off a revolution in trying to think about how we could actually go about building one of these exotic devices. This began with quantum annealing and adiabatic quantum computing in the late 90s, and a variety of candidates for the quantum transistor have come up over time, including superconducting qubits, ion traps, photonic approaches. There are many technology platforms that are being explored. But as of 2017, there are now cloud-based quantum computers that are available on the internet that was provided to us by this classical computing revolution over the last century. And a few years ago, we've even developed quantum advantage, which is to say we've performed, and in particular, the folks at Google performed an algorithm with a quantum computer that was significantly faster than they could have done even with the most powerful classical computers. So quantum computing is really at a transition point now, where it's moved from a scientific curiosity to a real technical reality. And this advance has required a whole lot of time and a whole lot of engineering. And we're in a really exciting place in the development of quantum computing now, where we can really start to understand how to make it work in a realistic way. So as I mentioned, there are a number of candidates for the quantum transistor, the basic bit of information that we use for making a quantum computer, but I'm going to focus today on superconducting qubits. And so I want to give you just a one-slide introduction to how superconducting qubits work and why they're useful. So a superconducting qubit at its most basic is a very simple circuit. It's a classical capacitance that's shunted by a nonlinear inductance that's provided by a Josephson junction. What's a Josephson junction? It's a superconductor that's separated from another superconductor by a small insulating layer. And this small insulating layer between these superconductors gives you just a little bit of nonlinearity in the inductance, which then means when you work out the quantum mechanics of the system, that the energy that it takes to go from the ground state to the first excited state is just a little bit different than the energy that's required to go from the first excited state to the second to the third, et cetera, et cetera. And this means that if we give the system energy that's at the frequency of the 0-1 transition, we're just going to keep the state within this lower two-state manifold rather than going up the ladder into higher excited states. And little bit of nonlinearity is just what we need to be able to treat this system almost as a two-level system, a 0 and a 1, which starts to look quite a bit like a bit. The really great thing about superconducting qubits is that unlike a physical atom, whose energy levels and couplings are defined by the rules of quantum mechanics, a superconducting qubit's energy levels, couplings, control properties are really defined by our creativity as experimentalists. So the capacitance of the qubit is set by this big plus in the middle here. We can make that whatever shape we would like it to be. Its coupling to a readout modality, its frequency, its state can all be controlled by lines that we bring in and signals that we apply to those lines. So a superconducting qubit system is a highly designable approach to making an artificial atom that we can control. Superconducting qubits were introduced in the late 90s, and over the course of the last 20 years, their performance has really improved exponentially. We used to think that there was something like an exponential scaling where, you know, the coherence times of the qubits were getting better and better and better exponentially over time. Now we seem to have sort of hit the limit of that, and we have to try other approaches to improving our systems. But nevertheless, the increase in performance from tens of nanoseconds in the late 90s to hundreds of microseconds for state-of-the-art qubits now has really been remarkable. And along that transition, as other quantum modalities have done, superconducting qubits have transitioned from a sort of physics experiment to really a commercial product at this point. And as that evolution has happened, we've had to deal with the challenge of interconnects. So what I'm showing at the left is a SEM image of a 5-qubit chip where the qubits are these plus signs. And there's a schematic of the chip at right, and you can already start to see what the challenge of interconnects means, right? So at the top in green, we have these meandering coplanar waveguide resonators that we use to measure the state of the qubit, which is critical. From the bottom, we have control lines that are enabling us to do single qubit and 2-qubit bit flips, phase flips, entangling operations, etc. And so these are absolutely critical for our ability to operate the system, but they also make it very difficult to make addressable arrays in 2 dimensions, right? So if I have control lines on the top and the bottom, then I can only really connect qubits in 1 dimension, and that's going to limit their connectivity and their utility. So this is an issue. And our solution to it is 3D integration. If you can't come in from the top and the bottom, then you can try to come in from above or below. You give yourself a 3rd dimension to access the system. So this 3D integration enables us to move the control and readout from beside the qubits to under the qubits, and it's a fundamentally enabling technology for superconducting qubits. And in fact, there are a number of companies, including IBM, that are using superconducting qubits as their modality for exploring quantum computing, and they are all using some form of 3D integration in order to access the qubit from the top and the bottom in order to enable the qubits to be coupled to one another laterally and in 2 dimensions. So 3-dimensional integration is critical for superconducting qubit processors. How are we going to do it? So one approach that we can explore is multi-layer routing, and this really provides us a lot of flexibility. Lincoln Laboratory has developed a state-of-the-art planarized niobium process where we have up to 8 metal layers that are shown at the top here. We have integrated Josephson junctions that enable us to do active components, and these layers are planarized and separated to have very high consistency and yield. And in fact, we've fabricated circuits in this process with more than 800,000 integrated Josephson junctions. For example, this device that we're showing here. This is also very closely related to the process that we use to make traveling wave parametric amplifiers, which I won't talk about today, but which are absolutely critical for high fidelity readout of superconducting qubit systems. So multi-layer routing of this kind is a very promising route to enable extensible qubit control. And so one option, if our goal is to have high connectivity, is to take our qubit chip that we've been working over the last 20 years to make as high coherence as humanly possible, and simply flip chip it upside down on top of the superconducting multi-chip module that's made out of this multi-layer process. The trouble with this is that the dielectrics that we use to achieve this really nice planarization and really high yield are really death to the qubits. So the dielectrics will interact with the qubits. They will ask the qubit, what is your state? What is your phase? And the qubit will answer them. And as the qubit answers the dielectric, it loses the information to that environment. So integrating a qubit directly on top of a superconducting multi-chip module like this is going to create unacceptable losses. We're going to lose all of that work that we did to create long coherence times by the way that we're attempting to do readout and control. So instead, we're going to introduce an interposer tier that's shown here. We're going to make an advanced interposer that has superconducting metallization on two sides and superconducting thru-silicon vias to connect from one side to the other. And we're going to use that to provide the interface between the qubit and the multi-chip module. So now we have all of the advantages of this multi-layer routing, but we're separating the qubit electrically from all of the lossy dielectrics on that chip, so that we're not risking qubit lifetimes by achieving this multi-layer routing. So this interposer tier really trades increased circuit and fabrication complexity for the ability to increase the density of our qubits and for improved qubit performance, even when we're using this multi-layer routing capability. And so this is the essence of what we call the three-tier stack: a qubit tier, an interposer tier, and a superconducting routing chip. It gives us access to very dense wiring layers. It provides a very large mode volume for each of the qubits so that they reduce their losses due to the dielectric. And it enables us to optimize all of these layers independently, so we can use our highest quality fabrication for the qubit tier, our multi-layer planarized process for the routing tier, and develop new processes to optimize the interposer tier. So with that introduction, I'm going to go in this talk through three main topics. In the first topic, I'm going to talk about some of our initial 3D integration demonstrations that really gave us confidence that we could make this three-tier stack a reality. I'm then going to talk about our thru-silicon via interposer and highlight some of the many uses of this tier. And then I'm going to show some exciting new results vetting the full three stack for superconducting qubit applications. So let's start with our initial 3D integration demonstrations. So before we go to full 3D integration, I want to highlight a 2.5 dimensional feature, which is an on-chip feature, which is superconducting airbridge crossovers. So these are really neat little on-chip links that you can use to hop into the third dimension just for a little bit, for a few microns, in order to jump over active lines, to connect sections of ground, and even to loop qubit squids physically intertwined with one another so that you can achieve very strong inductive couplings due to the mutual inductance between them. We developed superconducting airbridge crossover processes, and they're really enabling for these sort of small scale arrays of qubits. So what I'm showing at the right here is a 16 qubit chip that's on a 5x5 millimeter die. And if you look closely, you can see control lines jumping over one another, coming into the qubit, readout lines that are passing over and under qubit control lines that are going in and out. And so this is sort of a first level of 3D integration that allows us to route lines over and under one another without requiring full flip chip capabilities. And so this is a really useful capability that is actually even consistent with some of our more advanced 3D integration capabilities. So that's the first step, and that gets us to small scale arrays. But if you look at this chip, you'll also notice that there are wire bond paths in the center of the chip, right? So there's only so far that an airbridge crossover process can take you. At some point, the density of the signal routing is such that you really just need a second tier of metallization in order to bring the signals in and out. And so for that, we're going to use flip chip. The approach that we use is an indium bump bonding process. So you can see a SEM image of the fabricated indium bumps at the right here. We take two chips and deposit underbump metallization that's titanium, platinum, and gold on both of the chips. And then on one of them, on top of that, we deposit indium. We then smush the two chips together. You can see a cross section of those bump bonded chips here. And we use infrared imaging to vet our alignment, which is typically within about a micron. So this is our indium bump bonding process. And the first thing we want to validate is that we have good DC connectivity. And the way that we do this is we make these daisy chains where we're going back and forth, back and forth, back and forth between the qubit tier, the interposer tier, the qubit tier, the interposer tier. And we're carefully calibrating the resistance of those chains in order to vet both the yield of the bump bonding process, because a single missing link in that chain will mean that the whole chain isn't open, and in order to understand any residual resistance in the line. So we measure about 240 nano-ohms of resistance per bump, and that's basically consistent with our estimates of the resistance in the underbump metallization. And we measure chains of thousands of bumps in series, and we've measured at this point now hundreds of these chips, and have found this to be a highly reliable chip-to-chip galvanic coupling. So our indium bump bonding process is very reliable for mechanical and electrical connectivity. Of course, the next question we want to ask is it consistent with qubits? And so we do a test with flux qubits, which have great applications in the quantum annealing space. And so we take on the left here a single chip, which has been fabricated to be compatible with bump bonding integration, but is not yet bump bonded. So we have sort of the interposer top off. And we measure several of these qubits, and we find an average T1 of about 14 microseconds. We then perform the flip chipping process. We do the bump bonding, compressing, etc. And you can see at the right here the alignment between the qubit on the left and the flux control line on the right. And the T1 essentially doesn't change. 15 is essentially statistically the same thing as 14 for these qubits. So we find that the qubit coherence time is preserved following flip chip integration. And this tells us that our concept of the 3-stack is heading in the right direction. We can integrate qubits with a second tier without compromising the performance of the qubits themselves. So now we want to take it one step further, and we want to say not just, can we do this flip chip integration, but how reliable can we make it, and how controllable can we make it? Because that will be important for vetting our applications for this flip chipping. And so in particular, we're concerned about the tilt and spacing between the chips, because if the interposer is tilted across the chip, that can affect the qubit frequency, because the capacitance of the qubit will be slightly different across the chip. It can also affect couplings between the interposer chip and the qubit chip, which is important for setting the way that we control and measure our qubits. And it also can affect the spectral spacing of our readout resonators. So for example, if we take a qubit chip, again, that's flip chippable, but it doesn't have the top on it, and measure the resonator frequencies, in this case, they land between about 7.5 and 7.8 gigahertz. When we then add the interposer on top of it, the frequencies shift down as we expect, but we also can see some of the resonators, the frequencies come a little bit closer together. And this tells us that there's a little bit of an inconsistency in the spacing between the interposer chip and the qubit chip that's causing a slight change in capacitance in that area. And so if you have a 5-micron chip with, let's say, a 500 to 250 microradian tilt across the chip, that's going to lead to an average difference in height across the chip of between 1 and 2 microns, which is really quite a big difference when our intended spacing is about 3 microns. So that's the best that we can get with just indium bumps. And so if we want to get an improvement in the tilt down to 100 or even lower, we're going to need to find a new approach. And so the approach that we're going to take is to etch hard stop spacers into the silicon in order to have a physical control for the spacing and the tilt. So how do we do this? We take our qubit chip, we etch posts into the 4 corners that stand up vertically. We then do all of our qubit processing. We deposit Josephson junctions, we make our airbridges, we deposit underbump metallization and indium bumps, and then finally, we add the interposer chip on top. But now you can see that the spacing between the chips isn't just set by our ability to control the process and the amount by which we compress those indium bumps. It's really set by this physical barrier at the edge of the chips that says this is the way that this is as far as you can go. And so now the tilt in the chip is essentially set by our ability to fabricate these bumps uniformly. So we can look at the uniformity of those posts, and we measure this across a 50 millimeter wafer. And you can calculate from those measurements across the wafer what the tilt angle would be across a 5 by 5 millimeter chip. And those tilts are shown at the right here. And when we average them together, we get an average tilt angle of about 11 microradians for a 5 by 5 millimeter chip, which is basically an order of magnitude improvement over what we could get without the posts. So to give you a sense of what this looks like, you can see a silicon hardstop post in the corner here that's surrounded by indium bumps that are these arrays of 3 by 3 circles on top of an underbump metallization. We can flip chip these together and take cross sections, and we can see very nicely the indium bump bond connections. And you can see the contact that the silicon spacer is making with the interposer chip very nicely here. So we're making very good physical contact. And of course, we also for this want to ensure that it's consistent with high quality qubits. So here, we're going to take, again, a flux qubit, and we're going to put a silicon hardstop spacer post right next to the qubit. It's about 350 microns away from the qubit loop itself. And we have very good coherence times, 45, 55 microseconds, T1 and T2. And so this tells us that the silicon spacers are effective at enabling us to set good spacing between the qubit and the interposer tier. And importantly, they're compatible with the fabrication of long-lived qubits. So that tells us that our qubit tier fabrication is up to snuff for the 3-stack. We have superconducting crossovers that allow us to do a little bit of signal routing on the qubit tier itself. We've done flip chip integration and have verified that we can support long-lived qubits in the flip chip, and we've done an additional process innovation of these silicon hardstop posts that enable us to really carefully set the spacing between the qubit tier and the interposer tier. And so with that done, we're now ready to move on to the second layer of the 3-stack, which is the interposer tier. And so that brings me to part 2 of the talk. We're going to talk about thru-silicon vias, the interposer tier, and the many ways that we can leverage this process innovation. So let's talk a little bit about the advanced interposer tier. It features 2 sides of metallization. We have aluminum on the qubit tier facing side and titanium nitride on the MCM facing side and in the TSVs. We also have the ability to deposit Josephson junctions on the qubit tier facing side of the chip, which we'll talk about a little bit later. And we can do underbump metallization on both the top and bottom, which is important for the 2-sided bump bonding that we're going to be talking about later in the talk. And the key innovation here is really the ability to do superconducting TSVs. So what I'm showing at left here is a cross-section of a wafer sort of halfway through its fabrication. And you can see as you come down the side of the TSV, we have really nice metallization going over the lip of the TSV, down the side, and all the way down to the bottom. So we have really good metal coating all the way down the TSV. These TSVs are very high aspect ratio, so you can see here. They're quite narrow. They're about 10 to 20 microns on a side compared to about 200 microns deep. So the aspect ratio is quite good. And this aspect ratio is important because it allows us, as you can see on the right here, to integrate these TSVs directly into active elements of qubit control. So this feature here is a flux control line that's TSV integrated, where we're bringing signals, flux signals from one side of the chip down to the other. You can also see sort of in the corners of the field, TSVs that are used to connect the ground on the top and bottom metallization in order to short out any chip modes that might exist. And it's really important, as I said, that these TSVs be very high aspect ratio in order to do this. So for example, if we had a TSV with 100 micron radius, we would be able to bring signals in from one side to the other of the chip, but we wouldn't be able to do, for example, this very nice microwave control to get the 50 ohm transition from one side of the chip to the other really well. You kind of need a bunch of TSVs that are organized related to one another in order to get a really nice 50 ohm connection there. So with 100 microns, you could pass signals, but you might lose some signal fidelity in the process. With 500 micron TSVs, that's essentially the size of the qubit itself. So now you either are not able to use TSVs to pass signals, and you can only use them to connect ground from one side of the chip to the other, or the pitch of your qubits, the spacing that each qubit occupies on the chip, just goes through the roof. And so you need much larger chips, or you're limited to many fewer qubits. So the aspect ratio is very important, and it really enables us to do small form factor signal routing. I'm not going to get into the details of how we manufacture these, but the first thing that we want to do with these devices, just as with the indium bonds, is to do daisy chains to vet the connectivity from the top to the bottom of the interposer tier and back again. So we're weaving back and forth up and down the chip. And similar to the indium daisy chains, these are tests of our yield and reliability of the process. Because again, if there is a single broken link in even one of these 3200 link chains, then the whole chain will look like an open. So we can measure the critical temperature of these chains. So as we cool down, we go through first transition at around 3.1, 3.2 Kelvin, and that's the tinitride thin film transition. We then have a sort of broader transition that occurs between 1 and 3 Kelvin, and that is essentially the tinitride that's in the TSVs themselves. It has a little bit of a different critical temperature than the TSV, than the tinitride in the bulk. And then you can't even see it here, but if you zoom in, you can also see the transition of the aluminum that's on the qubit tier facing side of the interposer. So we verify that they're superconducting via looking at the critical temperature, but we can also measure the critical current, and we measure this for, again, chains that include thousands of links of TSVs. We've measured, dozens of these at this point, and they have critical currents that are in excess of 10 milliamps. So this is a very high yield process, and it's important to have these kinds of critical currents because we want to be able to apply DC current to these lines in order to control the frequency of the qubits and perform quantum operations. So we test this by integrating the TSVs directly into qubit control lines. So for a first example, we're going to take a flux bias line, which we use to apply magnetic flux rather to the qubit in order to tune its frequency. We're going to pass that current from one side of the interposer to the other via one of these TSV interrupted flux bias lines. So we've done this, and we can see these U-shaped features are the qubit frequency tuning through a resonator and back up, through a resonator and back up as you go, as you increase the bias current. So this means that we can tune the qubit through multiple flux quanta well within the critical current of the TSVs, which is at a minimum 10 milliamps. So this tells us that we can perform DC qubit bias from a separate chip, from this interposer chip, using TSV interrupted flux bias lines without causing heat, without causing additional noise, because the TSVs are indeed superconducting. We can also do a similar measurement where now, instead of having a TSV interrupted flux bias line, we're going to do a TSV interrupted resonator. And so the resonators are what we use to measure the state of the qubit. They have to be able to carry very high fidelity microwave signals, because otherwise we won't be able to extract the state of the qubit very well. And so we want to verify that a microwave transition using these TSVs is also a reliable feature. So we do this. What I'm showing at the right here is single shot readout of a qubit that's measured through one of these TSV interrupted resonators. The blob on the left is a number of counts where the qubit was prepared in the ground state, and on the right is the qubit prepared in its excited state. You can see some smearing between the two of these. These are cases where the qubit was prepared in the excited state, but decayed to the ground state during the process of measurement. And we can fit these and develop a separation infidelity, which basically says how good is the measurement, which is distinct from how good are the qubits. And so we get a separation infidelity in 2 microseconds of readout of about 10 to the minus 5, which is very good. So this tells us that the TSVs do indeed support high fidelity microwave signals and enable us to do high fidelity qubit readout, which again is a very critical use case for our advanced interposer with TSVs. Now, the fact that we can do high fidelity readout also enables us to ask a very important question about the 3-stack, which is, can we make the qubits cold enough through the 3-stack? And this turns out to be a non-trivial question, because if you look very carefully at the way the qubit chip is connected to a thermal sink in this system, we essentially have, gold bond pads on our copper package, that's the thermal sink, but we're going through aluminum wire bonds, which are superconducting, up and down through the interposer tier, all on superconducting lengths again. Then we go through indium bump bonds, which are very low loss. And so the qubit's only connection to the thermal sink is through essentially superconducting connections, which are very poor thermal conductors. So one of our questions about the 3-stack was, is the qubit chip going to get cold enough to act like a good qubit, or is it just going to be very hot, which introduces a lot of noise and may impact coherence times? And so the fact that we can do single shot readout on this system enables us to essentially take the temperature of the qubit chip. And we find that the temperature of the qubit chip is about 50 millikelvin. Now, this is a little hotter than the dilution refrigerator in which we perform these measurements. The dilution refrigerator, is typically about 10 millikelvin, but 40 to 50 millikelvin is consistent with what we see for our standard qubit chip, and really has to do with non-equilibrium quasi-particles in the system, entirely separate from the ability of the chip to thermalize. So this tells us that the qubits are thermalizing consistent with the single tier process through these multi-tier superconducting connections. And again, this is just providing us more confidence that we're on the right track with the 3-tier concept. Okay, so we've done DC control of qubits. We've passed microwave signals through the TSVs, and we verified that a cold qubit stays cold even when it's measured in a multi-qubit stack. So now we want to ask the question of, instead of just sort of taking our standard readout and control modalities, how can we use the superconducting TSVs to do fundamental redesigns that enable us to do more compact or more functional circuit designs? And one of our first targets is going to be the readout resonator. So the readout resonator, we've seen a few of them. This is essentially a quarter length meandering coplanar waveguide resonator that couples to an output line on one end and couples to the qubit on the other end. And the full length of these resonators needs to be on the order of a few millimeters. So even when we meander them like this, they still take up a lot of physical space on the chip. So this one takes up about 1.25 millimeters. And that's in comparison to the qubit itself, which is about 360 microns on a side. So the resonators are much larger than the qubits themselves. So this is one of our first targets for using TSVs to do a fundamental circuit element redesign. And the way that we're going to do it is we're going to make a lumped element resonator that has essentially a spiral inductor on the titanium nitride side of the TSV chip that connects down to the qubit via a TSV that provides significant capacitance to the resonator itself, and also provides a capacitive coupling to the qubit. And so if we put an image of this to scale on top of the qubit, as we see it left here, these compact lumped element resonators, which we call colloquially circle resonators for obvious reasons, they're really about the same size as the qubits themselves. So now we have the opportunity to do readout from above that's really at the same size scale as the qubits themselves. So we've made these. We measure the internal quality factor of the resonators themselves. They're at about 400,000, which is quite good. We perform similar experiments as we saw a few slides ago to measure the single shot fidelity of the measurement, and we find the separation fidelity in excess of 99% in 2 microseconds. So we have very good readout. And of course, we want to verify that the use of these circle resonators doesn't damage the qubits. And so we measure transmon qubits with T1 of about 40 microseconds as read out using one of these circle resonators. So this checks all of the boxes for us, and it tells us that we can do vertical readout that's integrated at a pitch equal to that of the qubits because we have access to these TSVs. The next thing we want to try is to try putting qubits on the surface of the interposer itself. If we were able to do this, it would enable us to do denser qubit packing because it would allow us to have 2 layers of qubits very close to one another. We could do very strong qubit coupling due to the parallel plate capacitance across the 2 tiers, and it would enable us to do a variety of chip mode reduction techniques. But the interposer goes through quite a lot more fabrication than our standard qubit chip does. So we want to ask the question of, can this surface of the interposer support coherent devices at all? So we're going to put qubits on top of the interposer, and we're going to look just at the interposer tier for now. We won't be doing bump bonding for these experiments. And what we do is we fabricate, again, flux qubits on the TSV interposer surface, and we see that they have coherence times in excess of 10 microseconds, some up to 20, and we're actively exploring what the limitations of this are. We don't think that this is the limit of this process at all. But even if this were the limit of the process, this would still be extremely valuable for things like tunable couplers, annealing qubits, and more importantly, it really validates the idea of doing biplanar chip designs that have active elements on multiple surfaces. So this was a very exciting development for us. And it also opens the door now to, since we've used TSVs to make the resonator much smaller, we can start asking questions of, well, can we use the TSVs to make the qubits themselves much smaller? And so this device that looks a little bit like a candlestick is essentially using the capacitance within a TSV itself, shunted by a Josephson junction on the surface of the interposer tier, to make essentially a parallel plate capacitance that allows us to make a very small qubit. So you can see uh, here and zoomed in on the right, an image of one of these qubits. The capacitor pad now is essentially 20 microns by 50 microns on the other dimension. And we can put it on top of our standard qubit over here, and you can see it really is very tiny. This is a dramatic reduction in size. And we've measured some of these devices. Our preliminary data from our first run, we measured transmons with about 25 microseconds of T1, flux qubits about 12 microseconds. And again, we don't think that this is the limit of the coherence on these devices. But this really demonstrates to us that we can make TSV integrated qubits with an order of magnitude reduction in the qubit footprint. And again, even at the coherence times that we have now, this is already useful for things like tunable couplers, annealing devices, etc. So this was a very exciting development. So to summarize part 2, I hope I've convinced you that through-silicon vias are very, very useful. The fact that we have superconducting transitions from the top to the bottom of the tier, and the fact that we have very high aspect ratio for those transitions enables us to integrate these TSVs directly into our signal routing, both for controls and for readout. We also can use them to fundamentally redesign both our resonators and our qubits to make them more functional within this 3-stack architecture. And we think that future applications abound. We can use them for couplers, filters, etc. We think there are all sorts of ways that we can fundamentally redesign our control modalities to take advantage of the unique features of this interposer tier. So that brings me to part 3, looking at the full 3-stack. So we've done some innovations on our qubit tier to make it ready for 3D integration. We've demonstrated and embedded the interposer tier. Now it's time to bring them together with our multi-layer processing step. And so, of course, the first thing we're going to do is we're going to check on mechanical integration. This is a highly non-trivial process. It requires us to do very well-aligned indium bump bonding now between 3 tiers. And so I'm showing now a confocal image of a fabricated and bonded full 3-stack, where the blue is the multi-layer routing chip. In green, just underneath, is the TSV integrated interposer, and in orange at the top is the qubit tier. And we can dice these in 2 and get a cross section, and we can see very nicely the 3 tiers, the indium bump bonds that connect them, and the TSVs that take us from the qubit tier down to the SMCM. So this is our first demonstration of the 3-stack with our superconducting TSVs and these 2 bump bond connections. Our next step after mechanical connectivity is to check on DC connectivity. So now we're once again going to do our daisy chains. So we're going to start from the control chip, the SMCM, go all the way down to the bottom of the multi-layer stack, all the way back up, through bump bonds, through TSVs, through bump bonds again, to the qubit tier, all the way down, all the way up, back and forth, again for thousands and thousands of links. We've measured several of these daisies chain stacks now, and we've found across the board that we get more than 10 milliamps of critical current across several of these multiple 3-tier stacks. So it's a very high yield process, and we're very happy to see this. One thing I'll note is that you may be asking the question, well, you have normal metal in your underbump metallization, so how are you getting critical currents? We actually find that the underbump metal is very well proximatized by the indium, by the metal underneath. So we actually are able to measure essentially the critical current of the full chain. So this gives us a thumbs up from the DC connectivity, from the reliability aspect. And so now the next step is to integrate with qubits. So we're going to do that. We have on the SMCM tier are both microwave and DC signal routing, because we want to check on both of those. And then on the interposer tier, we have most of our readout and control. So we have 10 resonators, we have all of our local flux bias lines, and we have 5 C-shunt flux qubits that are on the qubit tier facing side of this chip. Again, highlighting that we can actually put qubits on the interposer. And then on the qubit tier, we have a set of an additional 5 flux qubits. And we smash these all together. We do our 3-tier bump bonding, and our early results say that this works. So we measured T1s on the order of 20 microseconds, T2 on the order of 35 microseconds. Again, these are flux qubits, and this is our first attempt at this experiment. And so we see already that the lifetime and coherence are consistent with what we get for standard flux qubits within the single tier process. So we're very happy with this first demonstration, both of qubit readout and control using the full 3-tier stack. And this really validates the whole underlying principle of what we've been developing over the last several years, that we can have a qubit tier, a signal routing tier, and an interposer to connect the two of them, and it all works together and supports high coherence qubits. And so then, of course, we can integrate this into small-scale multi-qubit devices, which is what we want to be enabling all along. So what I'm showing here are some details of our quantum annealing testbed device. This device was designed and initially tested by Northrop Grumman under the QEO and quantum annealing feasibility study programs, and it's currently being operated by Lincoln as a testbed for the RQMLS program, all of through DARPA. This device has 25 capacitively shunted flux qubits. It has independent X and Z control on all of the qubits. It has very high fidelity readout on all of the qubits using both the interposer and the multilayer routing chip. We have 40 couplers to connect all of the qubits, and so this is essentially the stage at which the 3D integration capability is really going to shine. This device would absolutely be infeasible if we did not have access both to the routing and to high fidelity qubits with the interposer to enable us to connect between the two of them. So we're in the process of calibrating this device for the RQMLS program, and we're really excited to kick the tires of it and put it into action. So with that, I will summarize. I hope I have convinced you of the utmost importance of doing 3D integration as we move to small and medium scale arrays of qubits. We've talked through the flexible and very capable interposer tier that has very good yield, very good DC and RF transitions from one side of the chip to the other, and enables us to do compact resonators and qubits and more. And we've also, for the first time, vetted the full 3-stack. We've shown very good critical current through thousands of transitions up and down across the whole 3-stack. We can do qubit control and readout. We have coherent flux qubits that we can fabricate in it, and we've integrated, or we've used this 3-stack to create quantum annealing testbed devices that are really going to push the state of the art in that area. And there's a lot more to do, right? So we have compact qubits and resonators. We want to integrate them together into arrays. We think there's a whole lot more unexplored territory in truly 3D integrated circuit elements that take advantage of the dimensionality, both of the interposer and of the multi-chip module. And we've only started to scratch the surface of what we can do with the full 3-stack control and readout. So it's a very exciting time at Lincoln Laboratory, and I'm very excited to see where we take this over the next few years. I have to acknowledge the extraordinary team of people who are doing this research, both at Lincoln Laboratory, and you can see the team here, which has actually grown quite a bit since we took this picture. We haven't been able to gather in groups that dense for the last 18 months. And the incredible scientists in the engineering quantum systems group at MIT, who we work very closely with and have been real partners in developing and vetting this technology. I also really want to acknowledge all of the staff and technicians and process engineers at the Microelectronics Laboratory. They've really been critical in making the Interposer Tier and the multi-chip module chip a success and a reliable process as it's become today. So with that, I'll put back up my summary slide, and I'd be happy to take your questions.
Thanks, Molly. That was a fascinating presentation. It's so nice to see the hardware of superconducting qubit modality in such depth, like how you build this, what kinds of efforts it takes, and the size of the teams it takes to make this kind of work possible. So please drop your questions in the chat. And while you're doing that, I wanted to get your perspective on something, Molly.
Sure.
Having worked in 3D integration as well before, I kind of think of, this is a very similar to processes that were developed during classical computing, very much with like CMOS and stuff like that. But the requirements kind of are quite a bit different for superconducting qubits. So instead of maybe the density and thermal management you care about for classical processors, here you care about having electromagnetically engineered 50 ohm transmission lines so you don't get spurious reflections that can cause crosstalk. You care about everything being superconducting, like you said, you're proximatizing the underbump metallic, for example, which was going to be one of my questions. And you do care about thermal management because you do need to get these cold. So I was wondering if I could get your perspective on the differences, maybe, or your take on superconducting qubit integration.
Yeah, it's there are always things that we can learn from classical electronic processing. And one of the really great things about the Microelectronics Laboratory is that, it does CMOS processing, it does superconducting electronics, both classical and quantum. So there's really a great depth of experience and built up knowledge that exists in the facility. But there are differences, right? You can't use normal metals in a superconducting qubit system because you inject quasi-particles into your qubits and you destroy all of the hard work that you've just been trying to do to create coherence in the system. You have to be careful about the trade-offs between pitch and spacing and crosstalk, right? So there's all sorts of different considerations that have to be taken into account when you're thinking about, is this a process that I can port directly from classical electronics into superconducting qubits, or do I need to take a few steps back and try a different route? And what we find works really well is to take people who have come from that kind of a processing and process development environment, teach them about the requirements of a superconducting qubit system, and basically let them take all of the knowledge and the techniques and the development mindset and apply it to a new set of requirements. And that's worked phenomenally well for us at Lincoln.
That's great. So we do have a question in the chat, and it is similar to one of the ones I had. So Jacob asks, could you explain how the TSV allows for the miniaturization of the qubit and readout resonator? And this was kind of my question, in that, you mentioned it, that you could have you have capacitively coupled qubits, from my understanding. And how would you align the qubits in a way such that you had these TSV qubits that could be capacitively coupled to each other, or they could be capacitively coupled through the air gap between your different stack or different components?
Really, really great questions.
Yeah.
Yep. So the compactness of the circuit elements actually also comes from the high aspect ratio of the TSV, right? So you have a very long, very lean, essentially capacitor. And so we didn't, in retrospect, this should have been very obvious to us, but where we really discovered it was in the first time that we measured these resonators. Because, we like to do step-by-step development. So our first step is we make, the landing pad in the middle of the resonator and the spiral inductor that goes around it, but we don't put the TSV in it. So we measured a set of those, And then we measured a set of resonators that had the TSV in it, and the resonance frequency of the device dropped by like a gigahertz, which tells us that there's a huge participation of the electric field in the capacitance of the TSV itself. So the TSV is really good at pulling electric field into itself, into the silicon, which then increases the capacitance. And if you have two of them next to each other, then you get the capacitive coupling between them. That's essentially a parallel plate capacitance, which is much higher capacitance than capacitances that are sort of side by side. So it's parallel plate, it's running through the silicon rather than through vacuum, so you get very high capacitances. And then the way that you connect them to one another is you can either put them in the TSV substrate itself next to one another, or you can, if you don't want that much coupling, you can connect them using these like side-by-side capacitances on one of the surfaces. And as you said, you can absolutely couple them from the interposer tier down to the qubit tier via just the capacitive coupling from one to the other, similar to what we do for coupling the qubits to the readout resonators that are on top of them. So there's a whole playground of applications that you can think about where you might want to have active elements on the interposer and on the qubit tier itself.
Yeah, that's amazing. That opens up a lot of possibilities. And so then I have to ask if you've looked at the 2-qubit gate fidelity between qubits that are coupled in this manner.
It definitely is something that we're thinking about. Yeah.
Okay, great. Let's check the chat. I think we have some general questions, but we can save those for the chat. In the meantime, I just want to ask you if there's anything that you'd like to plug yourself or for MIT Lincoln Labs.
Oh yeah, absolutely. We are, it's an exciting time in quantum computing. Lots of folks are hiring. We are certainly hiring. In our superconducting qubit team, we also have openings in quantum sensing, in ion trapping. So if you are interested in quantum and you have a US citizenship, I highly encourage you to go to careers.ll.mit.edu. I wish I had put it in my slides, but I didn't. Or, you know, I'm very Googleable. You can reach out to me, send me an email. I'd love to talk.
All right. Well, thanks again so much for presenting this work to our audience. And thank you, the viewer, for tuning in. And until next time, please subscribe so you get the latest updates on research and academics in the quantum community. And until then, I'll see you next time.